So the title of my talk is Think Big and as much as possible stay small. My name is Venkatesha Prasad. I work as an associate professor at Delft University of Technology. And the work that I'm presenting is a joint work with one of my colleagues, Dr. Sujay Narayana, who is also in this conference, has joined. And of course, my senior colleague, Chris Verhoeven. The satellites, if you look at this, right, so 1960s to what is happening now, is that you see the satellites are becoming very small, right? So if you look at 1960s, these huge big ones, of course, we are still launching many of them, but there is a trend which is making it smaller and smaller in size, as well as in weight. Some of the things like huge ones that we have is like 8,000 kilos. Then the small ones, the weather related satellites, and then the micro one, and then the nano satellites, which are of the order of 5 kilos. So that is how the evolution is happening. It is somewhat similar to what we see in the animal kingdom, so that you could see the capability, the physical capabilities, as well as what it can do, right? But when you go to very small sizes, that doesn't mean that you're not able to carry out some nice, important work. We all know that ants and the shoal of fishes, the bird swarms, they all do lots of things. They communicate with each other, they carry out things together, but they also keep individuality. And that is something that we are now going to see more and more, because you can have devices, the satellites in space doing their own job, but also contributing to the overall system as a whole. Exactly, that's what we wanted to see, though the sizes come down. And then the idea is to have swarms, right? And these swarms are supposed to really carry out things which are going to be very much necessary and useful together. Now, let us look at, let us say, what are the important aspects of swarms, right? So the best thing that we can say is that you have power in large numbers. So when you have a large number of satellites, even if you miss one or two, or if something doesn't work, so you don't have to really worry about, but together as a whole, you will be able to carry out a lot. And swarms actually give that capability. So to that end, we started our programs in TU Delft some years back. And this was our first satellite. And we wanted to also move towards something we call it as wireless actuator network in space, basically sensor wireless actuator network in space. So it's basically called as SWANS. And that is what something that we wanted to try and they do. So you could see that these satellites has got so many sensors as well as actuators. And we are trying to make it as miniaturized as possible. So some of the things that you see here is, let's say, a sun sensor, the antenna deployment system, and also a micro thrusters. So various things that flywheel we have. So lots of these things are going to be miniaturized. And the challenge is when you miniaturize, it's not that you just downgrade all the processors and capacities and then it still work. And that's not the case. So you have to really come up with something completely new. The idea is that we wanted to use these swarms. For example, I want to just give you one example. where we have a surveillance, right? So assuming that you have one big satellite, India has launched lots of these big satellites, but you could see that the turnaround time is going to be very small. So that means if you want to have a continuous watch on, let us say, some of the things, for example, in the sea, then you will not be able to track them. Now, you just do the same thing. For example, an object in Indian Ocean, which is moving, that you see in the middle. So if it is, if we have more and more number of these nanosatellites, the idea is that you will be able to really track them. See, the question is now, these nanosatellites are less capable, of course, compared to, let us say, a big carto satellite, wherein you will have almost like 1 meter accuracy, right? 1 meter resolution of the pictures that you can take. So the idea is that once you get a good picture of this and then get that 1 pixel or few pixels of something that we want to track, and that information would be given to these nanosatellites. So though the nanosatellites do not really have a big picture or a nice picture about the object that it is tracking, but it will track that 1 pixel. And that's enough before the next big satellite is able to come and then see. So that we should be able to track as well as be able to monitor. And this is just one example, but this can be, because this is an easy example to explain, that's why I took it. But there are many more examples that we can think of. For example, monitoring the weather, right? Whenever you see cyclone, how the climate is changing. For example, how the weather is going to change based on the movement of these clouds. So you should be able to watch and then update it in real time, so that we should be able to give warnings. We should be able to give accurate, let us say, weather report. Still, we have so many radars and others in Netherlands. Still, we see that sometimes we see that, okay, at 7:30 in the evening, it's going to rain heavily. 9 o'clock, nothing, right? So we have seen so many times such things. In Netherlands, we see lots of rains almost every week. So that's a different thing. Let us move forward. So the idea is that a big thing can be even lifted with small ones, these ants, right? So similarly, we can come up with functionality of the big ones using very small, low-cost satellites or even pico satellites. So the other thing that we are working on is, for example, it's called WOLFAR, orbiting low frequency array. The idea is that we want to have a swarm at some point, so that we should be able to watch what exactly is or what exactly has happened, let us say, during the Big Bang. So that means you should be able to really listen to the radio frequency coming from deep space in the range of 10 kilohertz to 20 megahertz. That is extremely difficult because of the low frequency. So probably we have to have these satellites having a sort of a constellation that can act as a big antenna array. Just imagine the satellites at exactly the same position, looking into the space, deep space, and then trying to coordinate with themselves and then listening to the frequency in the range of 10 kilohertz to 20 megahertz. Fantastic application. The idea is also to move behind the moon, but anyway, but at least it takes some more time, but it is doable, knowing how the world is moving these days. So to build the concept of swans, so something that we definitely need is miniaturization, and lots of computing and communication need to be energy aware. data handling, wherein you have to have distributed communication, and of course, time synchronization, localization, without which you will not be able to do. So now imagine, so we miniaturized it. So that means you have to somehow coordinate. So instead of one satellite, big satellite, doing one thing, wherein you just have to do everything in one satellite, now you have to do many things with multiples of them. So though you think that, okay, you got redundancy, now you have few more problems like time synchronization and then distributed computing, for example. And of course, energy aware computing, where because of the miniaturization, you will not be able to generate more energy. So this is one nice picture wherein TU Delft also gave or took part in building a nanosatellite. So you could see that how much harnessing that we have here. So you not only the boards, but you have to put all these wires inside when you pack it and then send. So instead of that, imagine if you are able to have a single port PCB acting as a satellite. You have multiples of them, and then they try to do things together if you are able to control their movement and then position them very well. There are multiple ideas and opportunities that we can think of, but the miniaturization is what you could see now as a contrast. At TU Delft, we built a very first nanosatellite, and ISRO was kind enough to launch this satellite in 2008, and it survived till last year. So almost 15 years it lasted. So this was a first satellite from TU Delft, successful, lived for 15 years, and then came back to Earth. And of course, we don't know where it is. It's burnt out anyway. So it's a CubeSat. And then we had amateur bands. You heard the ITU and other requirements when you want to use these frequencies. And also it was in sun synchronous orbit. And then we had our own Dutch space payloads and also a sensor and amateur transponders. And then it worked for 15 years, even though there were on few occasions, solar flare could have damaged it, but it still worked. And the wireless sensor on board, the Zigbee node that we had put it inside to test it. So that signal was caught by an antenna array in the Netherlands. So that is something very interesting that we had. And then we built Delphi next. And it had a very simple, if you could see here, it's a micro thruster. It was based on water, and few like 60 thrusts or something like that we could have. And of course, we also had solar cell degradation measurement that we had, transceivers we had from ISIS space, and also particle spectrometer that we built. So we had more and more payloads. And then again, it was launched from Russian soil, and lifetime of 3 months, it worked. Afterwards, it stopped. And then we started looking at whether we can have space robotics. And then this is one of the projects that our students are working with a simple payload, which is a camera, which is just 3 grams. And then it can autonomously sort of walk on the moon. And also it can communicate directly to Earth from the moon. So this is something that we were working on. We are constantly modifying the design and then coming up with better and better ones. I will show you something. This is a hex, but it is not as big as the Boston Dynamics built. So this is really small, which is of A4 size, but you see the advantages, right? So it can negotiate almost any type of terrain, unless otherwise it has got a huge roadblock. But at least we have, that's what you could see that, right? So if it hits a roadblock, then it goes to, turns around and then tries to find some other path. So it's a fantastic exploratory robot. What we are also working now on swarms of these robots. This is another thing that you could see. It can even negotiate an obstacle of its own height and multiple obstacles, and it can survive. And the nice thing about it is that even if it, for example, yeah, it is almost taking a payload of 5 kilo. So that's something that is amazing. But even if it is going to topple, it can still work. So this is something that TU Delft worked, especially Chris Verhoeven is working on it. And we also tested a very small one, tiny one, and this is on a simulated moon soil. So you could see that it can negotiate, it can walk on that very fine moon soil. Of course, it's simulated on Earth. The characteristics of the soil is almost similar to moon soil or moon dust. And you could see that it worked. For example, if I show you, yeah, I will stop here and then see, you could see that it is, the legs are nothing but simple rods. It is not even a properly built leg in that sense. For its weight, it can negotiate. That's the beauty of this. And then we built Delphi P cube. It's a pocket cube. It is just 5 centimeter by 5 centimeter by 15 centimeter. It has got a micro miniaturized propulsion system, of course, orbit control. And then it was, I should change my slide. It's recently launched. And then it worked, and it's still working. And then we are working on something called Space Pixel. It is a single board satellite, and this can also be utilized. It can also utilize this for diagnostic purposes for the big space systems. So it has got multiple applications. The fantastic thing about this is that now the development has been done. Then we tested it. Everything is working fine. Environmental test has also been done. And the size is only 3 centimeter by 2.5 centimeter. And everything is energy aware. And also it can, without electrical connection, it can measure current of a big space system, as well as also the voltage of the batteries. And that is going to be a fantastic thing, because you never know what is happening. So you cannot, the brain cannot sense itself, heart cannot feel itself. That's what there is a saying. So you cannot have draw the power and then measure the battery power if the battery power or the system is not working well, right? So you have this chicken and egg problem. So that's where this can work fantastically, but it can also be a nice standalone satellite. And lastly, we tested this, and there is a Mobicon paper. It's one of the topmost conferences in embedded systems and mobile networking. And there, this work won the first prize. Dr. Sujay Narayana was the lead author and who worked on this and designed this GNSS. And this GNSS is such a nice thing, which is again 3 centimeter by 4 centimeter, the first version. And it can, the time to first fix using this GNSS module or the GPS module is only 30 seconds. Just imagine when your nanosatellite is moving at, let us say, 8 kilometers per second, and if you are able to position or self-position its location in the order of milliseconds. Because once you have a first fix, there are no difficulties because the speed doesn't change, the orbits doesn't change. So that means you should be able to predict what exactly is the next location after a few microseconds. So that would be a fantastic thing. And we also have this as almost like 1 hertz measurement update. You can also make it 20 hertz, and it takes only like 300 milliwatts. And that is where this miniaturization is going to help. So I showed you already 2 of these things that we worked on. So we are still making new version of this, which is going to be almost like 2 centimeter by 1.5 centimeter size. So it will be like any other chip, just go and then mount it on a PCB and then it works. So that's something that we have done. And then recently, 2 of my students, they have a company called, I'm done, the last slide. 2 of my students, they have a small startup which is working on many of these IoT plus space subsystems. They are working with Dubai campus, providing a ground station there. And also another student in India who came back from Netherlands has a startup. So I'm hopeful that my students would be able to do much more than what I'm doing. So that's it from my side.